Hello! In a previous video, we applied the Generalized Uncertainty Principle to the momentum and kinetic energy operators and found that the product of the uncertainty of the momentum times the uncertainty in kinetic energy is greater than or equal to 0. So there wasn't a lower bound on the product of the uncertainties in this case, and that's to be contrasted with the usual Heisenberg uncertainty principle, in which the uncertainty in position times the uncertainty in momentum has to be greater than 0, namely greater than or equal to h bar over 2. However, whether you actually have definite states of both momentum and kinetic energy at the same time, namely, can you have simultaneous definite values of momentum and kinetic energy, depends on the state that you choose. So let's look at how that works out in a simple example. Let's consider the n equal to 1 mode of the infinite square well. So for the infinite square well, we have psi of x is square root of 2 over L, sine of pi x over L, and for this is an infinite square well between 0 and L. So let's calculate the uncertainty in the momentum. And in order to do that, we have to calculate the expectation value of the momentum and the expectation value of the momentum squared. So the expectation value of the momentum is just 0 in this case. The expectation value of the momentum squared, however, is not 0. And so when you calculate the uncertainty in the momentum, which is the expectation value of p squared minus the expectation value of p all squared, and taking the square root of that, you find that it is non-zero, which tells you that you're not in a definite state of the momentum. What about the kinetic energy? Well, let's calculate the expectation value of the kinetic energy and the kinetic energy squared so we can calculate the uncertainty in the kinetic energy. So the expectation value of the kinetic energy is, it turns out, non-zero. Actually, it looks a lot like the expectation value for p squared, and that's not a coincidence. The two are just related by a factor of 2m. Let's calculate also the expectation value of the kinetic energy squared. So we have to square the kinetic energy operator here, which means we actually get a fourth derivative rather than a second derivative inside of that integral. But otherwise, the calculation works out the same. I'm, of course, sparing all the details of taking the derivatives of the sign in each of these cases. But you should find you get something that looks like this for your result. If I then calculate the uncertainty in the kinetic energy for this state, I find that the uncertainty is 0. So this particular state is in a definite state of kinetic energy. It has a definite value of kinetic energy. It does not have a definite value of the momentum. Okay, so how do we understand this in the context of the uncertainty principle, which told us that the product of the uncertainty in momentum and kinetic energy had to be greater than or equal to 0? Well, actually, this works out perfect. We're even saturating this bound. So if you take the product of the uncertainty in momentum times the uncertainty in kinetic energy, so we have a non-zero number times a 0 number, and that just gives us 0. So in fact, we are exactly saturating the uncertainty principle. Just because the product of the two is equal to 0 doesn't mean we're in a definite state of either one of them. Okay, in this particular case, we were in a definite state of kinetic energy, but we weren't in a definite state of momentum. Can we be in a definite state of both momentum and kinetic energy? Sure, I think we can. We just have to be a little bit more creative about the state that we're interested in. So again, this all depends on the state that you choose. So let's choose a different state. Again, in the infinite square well, I'm going to choose 1 over square root of L e to the I kx. So let's calculate the expectation value of the momentum and the momentum squared, and then the uncertainty in the momentum. So the expectation value of the momentum in this case turns out to be non-zero. Actually, it's h bar k. The expectation value of the momentum squared is similarly h bar squared k squared. And so when I calculate the uncertainty in the momentum, I actually get 0. So this particular wave function in the infinite square well is a definite state of momentum. It's not one of our usual energy eigenstates, but it is a definite state of momentum. What about kinetic energy? Well, I can do the same thing that I did previously. I can calculate the expectation value of the kinetic energy and the kinetic energy squared. All I have to do is take some derivatives and then do some integrals. Okay, if I do those derivatives for the expectation value of the kinetic energy, I get h bar squared k squared over 2m. And the expectation value of kinetic energy squared, it looks like I get the same thing squared. So ultimately, I find that I have zero uncertainty in the kinetic energy as well. So I'm in a definite state of kinetic energy. So this particular state has a definite value of the momentum and a definite value of kinetic energy simultaneously. Again, compare this to the usual Heisenberg uncertainty principle and keep that in your head, where you're not allowed to have a definite state of position and a definite momentum at the same time. You could only have a definite value of one of them, for instance, and then the other one has to be infinitely less known in order to make the product be non-zero. But in this case, we're allowed to have the product of the uncertainties of momentum and kinetic energy be zero. And in fact, in this case, we have 0 times 0, which is indeed 0. So we're still saturating the uncertainty principle, but now we're saturating it by having a definite state of both momentum and kinetic energy. Okay, this was an example of how to apply the generalized uncertainty principle to momentum and kinetic energy operators, so to operators that are different than the usual position and momentum operators that we think of with the uncertainty principle.